We begin with the physical reality of a single relational database instance under extreme read and write load. CPU utilization spikes to 100%, and the system reaches its maximum compute and memory limits. Adding more RAM or a faster processor, a strategy known as vertical scaling, eventually hits a hard physical ceiling. A motherboard can only hold so much hardware, and upgrading components requires taking the database offline. Consider horizontal scaling. Distributing the dataset across multiple physical servers eliminates the single-node compute bottleneck. But relational databases like MySQL assume all data lives on one unified disk. Splitting that data across servers disables cross-node joins and standard SQL connectivity. Partitioning data across separate physical machines also fractures native ACID transaction guarantees. A transaction can no longer rely on a single local storage engine to enforce atomicity and consistency. To achieve true horizontal scaling, you must build an abstraction layer that maintains the strict illusion of a single, unified database to the application, while actively managing the complex distributed reality underneath. Distributed databases require strict rules to determine where data lives. A V-schema uses functions called V-indexes to assign row data to physical shards, based on a sharding key, like a user ID. Range-based sharding routes contiguous blocks of IDs directly to a single shard, but this creates data skew. A massive influx of adjacent keys forces one shard to absorb the entire load, creating systemic hotspots while others sit idle. Hash-based sharding provides a mathematical alternative. By passing the sharding key through a hash function algorithm, incoming data scatters evenly across all available shards, eliminating the hotspot problem. The trade-off is that sequential range queries become highly inefficient. Because consecutive records are now randomized, the system must search every single shard to compile a sequential list. Defining V-schema logic requires a strict architectural trade-off between query fan-out efficiency and optimal data locality. The application codebase simply cannot, and should not, maintain a map of this complex, ever-changing underlying shard topology. Introducing a stateless reverse proxy layer, like VTGate, it serves as the singular entry point, acting as a shield to hide the individual shards from the application. When the proxy intercepts the SQL query string, it converts the text into a branching, abstract syntax tree. Cross-referencing this against the V-schema, it determines the precise physical routing required to locate the data. If a parsed query requests data spanning multiple shards simultaneously, the proxy executes a scatter-gather routing process, dispatching the request to all relevant physical nodes in parallel. It then intercepts the multiple shard responses, merges the disparate result sets in memory, and returns a cohesive, unified response back to the application. The proxy layer successfully decouples query planning from data storage, masking the distributed reality and operating as a single unified engine. However, allowing a highly scaled proxy layer to communicate directly with backend databases introduces a critical vulnerability. You risk exhausting the connections on the database itself, causing the underlying storage engine to buckle under peak concurrency. This diagram shows the protective mechanism, the sidecar daemon. Processes like VT-tablet are deployed in a strict 1-to-1 ratio alongside every physical MySQL instance, intercepting all incoming connection lines from the proxy layer above. The sidecar's primary operational role is implementing connection pooling. This limits active connections, preventing the proxy layer from exhausting the memory limits of the underlying storage engine. It also provides query consolidation. Recognizing thousands of identical read queries hitting the sidecar at once, it merges them, executing only one query against the database and fanning the cached response back out to all requesters. Sidecar daemons act as the essential operational shield, ensuring the distributed proxy layer does not accidentally DDoS its own storage nodes. Even with routing solved, you face the distributed consistency nightmare, a single atomic business workflow that must update records on two separate independent physical shards. This illustrates the two-phase commit protocol. A centralized transaction manager coordinates phase 1, issuing a prepare command. Participating shards secure row-level locks, write to their logs, and vote to commit or abort by transmitting a signal back. If all shards vote yes, the coordinator issues the final XA commit, releasing row locks. But if the central coordinator crashes after phase 1, participating shards freeze indefinitely in a locked state, blocking all operational traffic to those rows. The saga pattern abandons distributed locks entirely. Shard A completes a local commit, triggering an event to initiate the update on Shard B. If Shard B fails, a compensating transaction is generated and routed back to Shard A to undo previous steps. Maintaining cross-shard consistency requires a deliberate architectural choice between the strict, fragile consistency of XA locks and the highly available eventual consistency of sagas. The ultimate operational reality of horizontal scaling is that eventually an individual shard will outgrow its capacity limits and must be split. This introduces the strict requirement of online resharding. Terabytes of data must be migrated and rebalanced across new nodes without incurring any application downtime. A stream-based replication engine runs directly between sidecar processes. The original full shard extracts row-based mortifications from a scrolling binary log and streams this real-time data flow into the sidecars of two newly created shards based on vSchema parameters. During the cutover phase, once the new shards catch up to the primary, the topology service updates. The proxy layer instantly reroutes traffic to the new shards, and the original shard is safely decommissioned. Dynamic, stream-based resharding automates database partitioning, replacing static, manual processes with an elastic lifecycle. This final diagram shows the complete constructed architecture operating in unified harmony under load, with data requests flowing smoothly through all decoupled layers. At the top, the proxy layer dynamically parses and routes queries based on the topology metadata. Beneath that, the sidecar daemons implement connection pooling and query consolidation, shielding the physical storage engines from resource exhaustion. This highly complex, decoupled architecture completely abstracts the distributed reality away from the application code. Splitting data onto different disks is only the first step. Achieving horizontal scale requires the active management of distributed state, topology metadata, and query routing layers.